Thank you very much. Is it possible to switch off these first row of lights because things are not clear? Follow me. That's on it. It's on. Hello. Hello.
Yes.
Hello. Yeah, it's okay. Okay, thank you all for coming here. Basically, this presentation is about what Mathematica is and how we can use Mathematica for parallel and CUDA programming. So, at Wolfram Research, we would like to think of Mathematica as one integrated environment which allows you to do a lot of things without having to go outside of Mathematica, right? So there are two aspects to this statement. The first aspect is that, in a typical work cycle, you want to do some coding, you want to get your results and then have it published and so on. But what happens is that you typically work on one particular software to do all your coding, you get the results, plots and everything. And if you want to write a paper out of it, you go into a Word document maybe and then try to write the entire paper. And then from there you want to make a presentation, you go into PPT and then transfer all of it into PPT and so on. This is a typical work cycle, but what happens with Mathematica is that you can do all of that in Mathematica, right? Right from writing code, running programs of course, and you can also create journal papers, you can have titles, headings, subheadings, references, and so on. People have written entire books in Mathematica. This presentation is also made using only Mathematica and nothing else, right? So it's all very, very easily possible. That is one aspect. The second aspect is Mathematica gives you the ability to do a lot of different kinds of programming areas. Numerical, symbolic computations, wavelets, image processing, statistics, and so on and so on and so on. Even within the base product, okay? You can see the CUDA programming, parallel programming, they are all included even within the base product. There is no need to buy anything extra, okay? A big advantage compared to any other system, I would say, to be very honest. Now, one question that often comes to us is, how does Mathematica compare to XYZ software? So I'm not going to address that particular question as part of this presentation. But if you're interested in that, you can talk about it later because it's a long discussion. If you're going to do a long discussion, I can have to show you some results, examples, compare one and one, and then actually it is not easy to make a fair comparison between software A and software B. You cannot be judgmental and say this is always better or that's always worse. It's very, very specific to what you're asking for. So I would not like to make a general categorical statement, but I would rather have a personal one-on-one discussion about it, right? So that's about, but probably what is really popular about Mathematica is its ability to do dynamic interactivity. What I mean by that is, I don't know if you can see this clearly, but let me reduce the size a little bit more. Basically, Mathematica allows you to create so-called dynamic interactive content. You can have a function in Mathematica called manipulate, which allows you to manipulate any number of parameters, however you want to manipulate them, right? Using that, basically people have created certain examples, right? For example, here is a population growth example. When you have certain number of foxes, certain number of rabbits, you want to find how the population would change after you run the simulation for certain amount of time. Or you have a mechanical engineering example of interacting gears. Maybe you can have certain number of two different kinds of gears. You can increase or decrease the number of teeth and so on, change the angle of contact, and then you can run the simulation and see how it moves. Or a signal processing example where you have a signal with certain noise content in it and you want to put in certain windows and you have to start filtering it, you can start zooming it inside and see. So basically these are all about different areas that you can use Mathematica for, and you can use dynamic interactive content. Now, the best part about dynamic interactive content in Mathematica is that you can deploy it to people who don't have Mathematica, right? You basically save this notebook as what we call CDF format, computable document format, and you send it to people who don't have Mathematica, right? And they would have to download the free player from our website, and they would open it up and they would be able to read through your entire notebook. Remember that Mathematica allows you to do textual writing also. You can have your titles, subtitles, section, the entire paper you can write with your equations, coding, and dynamic interactive content, and references, and so on, and save the whole thing as PDF, send it to people, they would be able to open it up and read the entire thing. They would also be able to play with the interactive content. The only thing they would not be able to do is edit the code. That is the only limitation, right? That's about that. Now, let us quickly jump into parallel programming in Mathematica and what Mathematica has to offer in terms of parallel programming. Basically, since Mathematica 7, we have had parallel programming capability, and it has been continuously improved. There are certain very fundamental functions that in Mathematica that allows you to do parallel programming, such as parallel map, parallel table, parallel do, and so on. So, I have to mention here that to do parallel computation on a single machine, you don't have to buy anything extra other than the base product. Typically, these days, every machine has at least 4 cores or 8 cores, right? So Mathematica allows you to do 4 or 8 subkernels you can launch on the single machine that you're working on, even with the base product. And you can start running your parallel computation along with those subkernels. And if you ever think of expanding it to multiple machines and so on, having an entire cluster and so on, then you'll have to buy what is equivalent to a parallel computation toolbox, right? That is what we call grid Mathematica. So you buy grid Mathematica, install it on a bunch of, let us say, 200 machines or so, but the code that you would need to run your parallel computing on all those 100 machines or 100 kernels would be identical to what you had to run it on this single machine. There is absolutely no difference, okay? The only difference is you will have to configure the kernels in the beginning. I will show you basically how to configure that in a single machine. But when you have multiple machines together, all you have to do is what is called cluster integration, and it will show you how many kernels you have from which machine. You have complete freedom to choose 10 kernels from here, 3 from there, 4 from here, and pool them all together into one big pool of, let us say, 700 or whatever kernels. Then you would just launch all those kernels and use parallel table, parallel map. The same code would work on all those kernels as well. So it is very typical for beginners and so on to test their programs on a single machine. The easiest thing to do, use just the base product of Mathematica, do your parallel computing on a single machine with 8 cores, run it and see if it optimizes, if it speeds up something. Then you can kind of have the confidence to kind of expand it out to so many other machines as well in the network environment, right? So obviously all of these functions are documented very well in the documentation center. You can actually click on any of these functions and just take a look at the documentation page for that. By the way, all the documentation pages are available both inside of Mathematica and they are all available online. Okay, lots of examples are presented. So let me illustrate one simple parallel program here. Let me do a couple of things. So if you click on the kernel config, let us see on this one. Evaluation. Typically, this is where you go and configure your kernels in Mathematica, right? At the moment, it only launches local kernels because this is a local machine only. But if you want to have a cluster integration, you could use either cluster integration or what is called lightweight grid. And basically, after you have enabled the grid, it shows you how many machines you have here and how many kernels within each machine is available for you. Okay, it is possible to dedicate certain number of kernels for certain users and so on. So you can actually pick and choose how many kernels you want. So basically, what happens is that once you have chosen to pick certain number of kernels, you can actually start launching your parallel code, which will do so presently. Let me start the task manager as well, which shows the CPU usage and so on. So it's a very simple program that I have to illustrate the point. Basically, I'm launching 8 kernels, as you can see here, launched 8 kernels, and then I'm running a simple evaluation on all the 8 kernels. Okay, that's really all I'm doing here. So let me just go ahead and run this code. You can see it is launching the kernels, and I want to show you the activity on all the 8 cores as well. So basically, after the evaluation is complete, you will see all the 8 kernels have been busy, and it shows you how much work each kernel has done, and you can basically see more or less even distribution of load and so on. It also shows you how much speed up we have, a speed up of about 8, close to 8. What happens is if you have 4 subkernels, the speed up is close to 4, and if you have 8 subkernels, the speed up is close to 8 and so on, but not exactly 8. There will be some overhead, right? We'll have to have some communication between kernels and so on. So it is not exactly 8, it is 7 point something. So it's pretty close to 8 times CUDA. So this is how it's very, very simple, nothing much to it at all. Now, again, as I mentioned, if you had, instead of 8 kernels, you had 80 kernels or even 800 kernels, the code would remain identical to this, okay? It would automatically, as long as they're all connected in a cluster environment, it would automatically talk to those subkernels and do it, okay? That's very easy, right? Now, I want to talk a little bit about CUDA here. Mathematica has supported CUDA programming for quite some time now, and both CUDA and OpenCL link, right? And I wanted to show you just one second here. So if you go to our documentation page, we support a lot of different NVIDIA cards. We also support OpenCL kind of cards. So let me actually show you one such example here. Basically, as long as you have one of these compatible CUDA cards, you are good to go, right? We support more than 100 NVIDIA cards. And I wanted to mention that part here that just because your card, if your card isn't displayed here, that doesn't mean we don't support it. It is just that it hasn't been completely tested, right? So we support a lot of different NVIDIA cards. The same with CUDA as well, right? So in OpenCL as well. So we support a lot of different cards, okay? Again, this is not the up-to-date list. They are updating this list presently with the new generation of NVIDIA cards. If you have any question about whether your card is specifically supported or not, feel free to send us an email. We have people from GT Enterprises here who are our local partners with Mathematica and NVIDIA. So you could talk to them or send me an email personally and I can actually look into it. What happens is that the developers do this testing in batches, right? So till the next batch of output comes out, you won't see anything updated here. But in the meantime, if you are interested, we can actually send you an information directly. Okay, so what is the advantage of using Mathematica for CUDA, right? Typically, you know, if you are not using Mathematica as a CUDA programmer, you would have to do all of this, right? Allocating memory, freeing memory, copying things, and so on. But what happens with Mathematica is that Mathematica makes it very, very easy for you. You would have to just write the CUDA kernel code. Everything else is taken care of by Mathematica. Okay, this is the first advantage. Secondly, for even beginners who don't know anything about CUDA, Mathematica already offers a lot of inbuilt CUDA functions. Okay, so you start with that. You don't have to write CUDA kernel code. CUDA kernel code has been written to you already, and you could use that to do your computations on GPU for certain areas, right? For example, here the listing of all the currently supported CUDA functions. We have a big list here. There are functions here in image processing, for example, image multiply, image divide, image convolve, and so on. There are also things in linear algebra like CUDA dot. There are examples in Fourier, inverse Fourier, and CUDA Fourier, and so on. Basically, we have plenty of CUDA functions already available to you, which are typically like any other Mathematica function. You could just use it exactly as they are. You wouldn't even know that it is a CUDA function, except for the fact that the function name starts with CUDA, right? This is how you do it, basically. But if you have to write your own code, which typically you will have to, because not every function is writable by anybody, right? You will need to customize everything. And so Mathematica also allows you to write your own CUDA kernel. You may have seen this kind of code all day, yesterday and today, probably even tomorrow. So you could just write your own CUDA kernel. There is a function called CUDA function load, which takes certain kind of arguments. And basically you apply that CUDA function just like any other function on the data that you have. Very, very simple, straightforward, nothing much to worry about, right? So again, Mathematica also supports multiple GPUs and so on, so it's very, very straightforward to extend your work on multiple GPUs. It is very common for people to combine parallelization and GPU programming all together. We support that as well. And as far as NVIDIA cards go, as I said, we keep on updating our list to more and more NVIDIA cards. If you have any questions, you can ask me that. So basically, I think that completes my presentation, right? So I don't have anything much. to tell you other than this. So if you have any questions about any of these things, please do feel free to contact either of us. It is very likely that I would be able to answer most of the questions. If not, I will talk to the developers who will give you more detailed, specific answers to you. Thank you all very much. Thank you. Any questions at the moment here? Right away, yes, please.
This kernel configuration, we write only the kernels, okay? But the launching is done by Mathematica.
Yes.
The launch configuration, the blocks and the grades. Is it calculated optimally by Mathematica?
No, no, no. See, you're talking about the one I showed you, right?
The last.
Right. Basically, you get to choose how many kernels you want from which machine. If you have a cluster of machines and you want to use some of those kernels from some of the machines, it gives you complete freedom for you to, I mean, of course, you could launch everything all at once and say, launch it on everything. That is also possible, right? But you may want to say, I want 5 from here, 4 from there, 3 from somewhere else, and somebody else may want to choose 6 from here and so on. So it is very possible to share the kernels of the same machine by different people. So you pick and choose how many kernels you want. All is always one option. Or you can say specify the number in that particular, you will have a machine name, all, and or a number to input. You can just put in 2 here, 3, and so on. And finally, you will have a big collection of, it will show you the total number of kernels. And you launch all those kernels using launch kernels, and then just submit your job. The distribution of job into the kernels happens automatically, and you get the result back, because the master kernel is the one that actually submits the jobs to each of these kernels, subkernels, right?
So
Yeah.
Is there a cheaper version for students for Mathematica?
Yes, there is Mathematica Student Edition available, which is not at all limited. The only limitation is the price. Everything else is identical to the original Mathematica, right?
Because I went to the site and I saw the cost, it was still pretty high. So
You could contact one of our GT enterprises guys. They could set you up already. Yeah, there is an academic version, there is student version, there is commercial version, and even within that, if you buy network, you will get some certain number of discounts and so on. So there are different kinds of ranges we have for that. Yes. Yeah.
As you said that we need to only launch the kernel, there is no need to copy the data. But
Yeah.
if there are multiple GPU cards, then how it will handle the memory transfer?
Okay.
Data transfer.
So if you have multiple GPU cards on the same machine that you want to use, typically a subkernel is attached to one particular GPU. Right. So you launch, if you have 2 GPU cards and you would want one subkernel to have contact with one of the GPUs and the other subkernel to the other GPU. That is how it typically works. I mean, there are ways to tweak it around. You can send me an email, we can send you more details about it, but for most purposes, each subkernel has its own dedicated GPU. That's how it works.
So user can decide which GPU card.
Yes.
And then accordingly.
Yes, absolutely. Thank you very much.
Thank you, sir, for the interesting talk. I would like to request Professor Dave to felicitate him with a memento. With this, we conclude today's workshop. The workshop will restart tomorrow at 8:30, so kindly be on time. And VIT staff and students, kindly stay back. And a gentle reminder, kindly check your names in the registration desk for any errors, because those names will be forwarded for your certificates.